welcome.
Thank you very much.
This lovely audience is desperate to hear what you have to say. It could be the salvation based on what Grace was saying about.
Yeah, you know. Well, first of all, can I kind of introduce myself? So my name's Peter Winstanley. I live in Scotland. I'm part of Semantic, which is a company based predominantly in the US, but also Canada and me. And I've had some chats with three of my colleagues who are named below as I was preparing this slide deck. We're a pretty small company made up predominantly, 20 odd ontologists. So, it's kind of an unusual mix of people. Some very interesting conversations that we have because we all come to it from different perspectives. So I've got some people who are kind of into philosophy and logic and analytics and metaphysics and things like that. Others who are computer scientists, others who are linguists. I myself came to it because I'm a clinical microbiologist and we spend all our time kind of trying to work out what microbes are. And actually, kind of curiously, I was seeing something in one of the offshoots of Nature talking about machine learning for microbiologists. And I was thinking, what, we've been doing numerical taxonomy since the Dark Ages. So there are a lot of things that, as we've been hearing about, have been kind of going round and round. And what I want to talk about is ontology, which to some extent has been going round and round for a long time. But first of all, I thought I'd kind of start off by asking ChatGPT what the heck was ontology useful for when it came to the world of AI. And so there's a bunch of different things: knowledge representation, data integration, contextual understanding, knowledge discovery, explanations. And ChatGPT seems to think that ontologies play a pivotal role in enabling the effective utilization of AI technologies, and so on. So the important thing for me is that what we do when we communicate is to make sure that we have words or symbols that reference things, and the things are kind of what we're thinking about. And unless what we're thinking about, stimulated by the words, refer to the same things, we end up with ambiguity, failure of communication. And the times when you've been chatting with somebody and you've reached a point where you realize that you're both going along divergent tracks and you need to kind of like reclaim that common ground and maybe replay what's been said before. So we're all kind of familiar with this semantic semiotic triangle. And quite often what happens is that we're using words that have got ambiguity. So the world that I inhabit is one where we use globally unique identifiers for things as part of the semantic web technologies. So we use IRIs, things rather than strings. And that then enables computers to kind of work with people, sharing the symbols that represent things, and therefore we've got the possibility of sharing thought almost. And when we start identifying things with IRIs, what we do is that we sort of begin to start saying, well, we've got classes and instances, and you'll all be familiar with this, but I'm going to rehearse them because I think it's really important. Because these are the core parts of an ontology and a set of linked data that the ontology gives us a mechanism for mutual understanding, mainly between people. And this is the critical thing. It's people that ontologies are there for. Machines come in second. And we've been doing this for an awful long time. So Plato had this idea of the idealized thing, which the stuff that we saw around us was kind of just a mere shadowy representation of. But Aristotle was beginning to sort of take a more grounded approach, having a look at things. So we're familiar with is early categorizations, the ontological square, and then the tenfold categorization. And then what we had was a whole pantheon of mathematical philosophers over the millennia who've been describing things, groups of things, ways of describing these classes as either types or sets or categories. And this sort of thing, a lot of people's eyes glaze over, but it's actually pretty important to remember that there are certain sort of deep mathematical things that underpin the way that we describe the groupings of stuff about us. And we have to use that if we're going to then begin to start using the sort of logical inferences that one can begin to start using within the description logics of OWL, which is the foundation of the semantic web. And it's the main tooling that we use in work in order to provide a description of the things of reality for people in their different enterprises. So in a way, what we're trying to do is to, as they say, carve nature at its joints. And the thing about carving nature at its joints is that in the main, across the world, we seem to be able to get considerable agreement on this. And Ernst Mayer's quote here about naturalists, whether it's Stone Age native of New Guinea or somebody in a more sophisticated place, recognizing species differences and things like that. It shows some aspect of our human discriminative ability to be able to sort of group things together into sets of like things. But the thing about it is that when you get into enterprises, there begins to be subtlety, and maybe some of the joints are a little bit more difficult to discern. And sometimes when you get changes of the way that an organization is pitched, you know, maybe the management structures change, things reorganize. And so the joints kind of twist around a little bit. But still, the thing about it, when we go into an enterprise, beginning to start making sense of what its information is that we're beginning to look for things that are similar, things that people within that organization would recognize as being separated by the natural joints that exist within their set of information. And from that, we begin to start working out an ontology on the basis of things with class, subclass relationships. But the other thing that's really critical here is to begin to say, well, what is not something else? So we have in the construction of ontologies, not only class, subclass, but also disjoints. The other thing is that we always accompany ontologies with natural language specifications. And these have got to be extremely well constructed. No circular definitions and that kind of thing. Because what we're wanting to do is to present in a formal way, in a computable structure, but also something that's very human understandable, a knowledge representation. And then what we can do is that we can get instances and assign those to one or more classes. And from that, we can make certain inferences up and down the class subclass hierarchy about those instances. The thing that puzzled me, looking at it from a historical perspective, is that it wasn't until the mid-1970s that people really started recognizing that actually relationships were really important. And Wood's paper to Harper, 1975, on what is a link, was one of the foundational documents of the developing model of what we call semantic networks. And so these properties that are the relationships between classes, or between instances of classes and other instances, or between instances of classes and literals, are critical for a whole raft of different things relating to what we've been talking about earlier. So the first thing is that they enable us to describe relationships that we can use for inference. And by that, what I mean is that we can specify some relationships as being symmetrical, so that if A is next to B, we can infer that B is next to A. Or they can be transitive. Company A owns company B and company B owns company C. Then in a transitive way, company A is owning company C. But the other thing about them is that they also enable us to specify the attributes of a thing. This comes back to my old microbiology stuff, because what we would do is to develop feature vectors. You've got an isolated microbe. How many sugars did it ferment? How many did it oxidize? Was it catalase positive or negative? Blah, 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 blah. And you end up with this great long feature vector. And we were doing this decades ago, and people are still doing it now. Because what we find in a lot of modern AI is that we still use things like random forests, with various ensemble methods of regression and so on, in order to do our modeling. So the specification of the semantics of the properties, these predicates, these attributes of entities, the definition of them is a foundational thing for the development of a pattern of AI, but it also enables us to use inference if what we do in our ontology is provide characteristics of those relationships. And again, properties in the same way as classes can be related to each other in a property-subproperty kind of relationship. The other thing that we can do is that we can specify, so properties are directed relationships. They've got an origin and insertion kind of thing, a lump bit and a pointy bit that they direct to. And so we can specify what types of things should be present at either the blunt bit or the pointy bit of the relationship, the domain and the range. So those are the things that are foundational to the ontology in terms of its structure. How we model an ontology, whether or not we're using the idea of types, which means that among the entailments, we can't say that a type is a subclass of itself, or we can use sets where we can include the entailment that it could be a subclass of itself. These are actually pretty important, although you only kind of realize it when you hit a wall. The other thing that we can do with classes is to say that there is a thing called an equivalent class. And you know the times in natural language, you know, somebody's been saying, oh, I saw this cat. You say, what's a cat? Oh, it's a mammal. It's got pointy ears. It's got retractable claws, a long tail, 4 legs, that kind of thing. So what we can do is take constructs that are made from other classes and properties and say that they are equivalent to another class. So how does that really help us? One of the things that it does is that it enables us to infer from data something, an instance, into a class. And we use that an awful lot. Sometimes you're never quite sure. You haven't got something in the enterprise saying this is a cat, but you've got this thing that's got 4 legs, retractable claws, pointy ears, and so on. And so you use inference with the specification of the equivalent class to put it in there. Now, the next thing that you can do with properties is to specify property paths. And that enables you to go along paths in a particular way, not necessarily taking too much notice of what the intermediate steps are, but you can then link together things that are separated along a particular type of path. And you can use that in 2 sorts of ways. One of them is that you can use it in an inferential way, so that you can then sort of say that I will create some additional linkage between something that is 3 lots of prepared before A, prepared before X, prepared before Y, prepared before B, and then you can infer something else. So this is part of a type of knowledge engineering, a sort of enrichment based on predicates, based on the ontology rules that you've got. You can add additional rules to define other things. The other thing that you can do is that you can use this as a form of search. And if you're working in graph terms, you know, either Sparkle or Gremlin, if it's a labeled property graph that you're using, or Cypher or something like that. It's quite normal in these sort of networks to be able to work across paths, not necessarily needing to know what the intervening entities are, and then to potentially create additional information. So the key thing is that what we have here, the ontology gives us ways, rules for understanding, developing context on a set of individuals, having an understanding of what inferences are possible, because this is something that people agreed, okay? The agreements of the ontology is between people, the action of the ontology is on data within a machine. We end up building what are called knowledge graphs. Knowledge graphs are a mixture of instance data and an ontology, usually in an RDF triple store, usually queryable by Sparkle. And so where does this lead us with search? I mean, one of the things that it does is it enables us to be very, very specific about the quality of the information that we use for things like training models of any sort. Okay, we've been talking a lot about large language models, but as I mentioned before, an awful lot of stuff to do with the identification of things, the operations on data sets is still done by things like ensemble methods, k-nearest neighbors in the vector space, and various other things, which have had a fairly long tradition, okay? The other thing about it then is that in addition to vector models, graph models can be used to provide both the augmentation and refinement of query, and they can be used for the guardrails when it comes to the results. And if you take a look at triple stores like Stardog, for example, already hitting the market with a combination of the triple store and the associated large language model interface. The other thing that we're increasingly beginning to see is the development of what's called causal AI. And RDF graphs are very similar to sort of belief networks, and one can associate transitions and probabilities and things like that with them. Causal AI is particularly important in developing things like industrial processes and so on. And we're seeing the development of companies specializing in this kind of work, like Parabol AI and so on. And so I think increasingly what we're going to be seeing is human-specified ontologies as an alternative to the clustering vectorization of text to develop terms that happen to be kind of like near each other in that kind of model. Because what we have with the ontology is the opportunity for, first of all, having people spending their time taking a look at what the core entities that they're dealing with, and addressing these in a very collaborative way across an enterprise, with the benefits that you get things like a corporate lingua franca, that you get the benefits of people using the same sort of chunks for their chunked thought. So you get better problem solving within the enterprise if you actually have something that people have contributed to, rather than something that's just been slurped out of a document set that has been used as a training set for the search process. And then the other thing about it is that the specification of predicates and the ability to use reasoning over predicates means that what you can do is provide expectations, and that you can provide other types of search where you're looking not for the entities, but for the relationships. Find me something that was prepared before something. Okay, I don't know what they are, but I can go through the predicate and find them. And so what you can do is that you can develop from the ontology a set of triple patterns that you expect to see. And this enables you to begin to start specifying, shrinking down your search space. I've been talking about ontological commitment, which is if you design an ontology in a particular way, you can't just take a bit of it. You have to kind of commit to the whole thing. And the other thing about it is that if I design an ontology that I've based on kind of sets, I can't really merge that automatically without being particularly careful about one that's been set up in terms of first order logic, for example, with types. And so you see different ontologies where you, so for example, the version 1 of the basic formal ontology, BFO, is first order logic, and that means that you end up with intractable computations for reasoning and things like that. And so what they've been doing is to prepare an LDL version, L description logic version, which gives you decidability, and you will be able to compute within finite time the entailments of your particular ontology. So merging ontologies is something of an art that's got to be practiced very, very carefully. And that has implications for the way in which we merge information automatically across different enterprises, for example. The other thing is that sometimes we don't want to create a fully fledged class. And what we do in semantic arts is to recognize that sometimes, if we've got an instance of a green bottle, it could be a type of bottle class and it could be a type of green class. But we really don't want a type of green class, because then we'll need a yellow class and a blue class and all the rest of them. So what we could do is that we could say that we've got a color class, and there's an instance of that that's green. And so we categorize our instance of green bottle. It's a bottle, but it's categorized by the color green. And these are ways in which we can model things using ontologies in a slightly different way to provide us with more efficiency and less kind of open-endedness. Because if we provide an additional class there, it gives people the opportunity of extending things in ways that need an ontologist to be doing the work. Whereas if we just have a bunch of instances of colors, it's very easy for somebody to sort of safely add a few extra colors if that's what they need. So the engineering of an ontology is something that we feel has to have a bit more than just machine input, because what you're looking at is the design of it for the purpose that it's going to be used, how it's going to be managed, and so on. When we talk about instance serializations, there are lots of different ways of doing that. But the key thing about it is that if we have shared semantics, we've got much lower data entropy, and therefore we've got enhanced compressibility of our data. So being cautious about not having an over-proliferation of predicates, being cautious about the way in which we create classes and so on, means that what we can do is have a full model of data, but with a high degree of compressibility. Ontologies, I think, and RDF bring everything into easy reach. We don't need to be kind of going trailing around all sorts of places, just like we would do in a buffet style on the left-hand side of the picture. Everything's kind of visible and within easy reach if we work with ontologies and a knowledge graph. And so the problem with that for an enterprise is that you've got to coordinate this kind of view. That we need to bring the whole enterprise into sharing its table, making sure that rather than each one serving up a bit of data through an API and people going around cruising the API space to see what they can find, what we do is that we bring people together, sharing stuff, making sure that they leave a bit of room for other people, coordinating their efforts and so on. And that's actually pretty good for enterprises. So my advice to ChatGPT, because it started off giving me some advice, is that ontologies are agreements between people in ways that machines can also use them. And they explicitly define these types and sorts of relations. And they can help us with our ChatGPT to restrict the search space, model the queries better. And we want ChatGPT to stop making a fool of itself and to give itself a reality check with what people think before it returns results. That's all I have to say.
Peter and I have a common interest in organs, musical variety. But when you do a search on some strange, like Google-like service, trying to separate out the organ that you and I know and
absolutely,
and the organ internal is one hell of a task.
It really is, isn't it? Yeah. And I think that this is the challenge with natural language and the ambiguity of words. And this is where moving as quickly as possible to the IRI space, if possible.
IRI?
Internationalized resource identifiers. Basically, what we want is for each of the particular meanings of the English word organ, we want to be able to get an individual IRI. Then we can cope with the lexical diversity because we can have multiple languages as labels of each of these indicators of meaning. It goes back to this business of the semantic semiotic triangle, that really what we want to do is to shrink down to a set of computer and human usable identifiers for each individual concept, so that we actually get that shared representation. And that then enables us to handle multilinguality and things in a search way perfectly adequately.
Questions too?
Just picking up on what you just said then, about having a separate identifier for each sensible word,
Yes.
which kind of brings back, I suppose, a sort of problem for natural language processing of word sense disambiguation, which we never really solved, other than the fact that we realised that there ended up being as many different senses almost as there were usages.
Yeah, exactly. But you see, it would be great if our dictionary providers like OEE and so on actually gave us a unique IRI for every meaning.
But they will disagree, the different dictionary providers, in terms of even how many senses a word has, let alone.
Exactly. Yeah. And so this is where these are human constructs. We have to have a different form of human librarianship.
Yeah. No, I get that. So, but I'm just saying, but do we need to be able to define all of the different senses and agree on the different senses
Within an enterprise.
in order to be able to do searching or something like that?
Well, within an enterprise, we try to do it for the main things, because, you know, that's the kind of closed world that we operate in. And that spills over into shared parts of the world. So when I, for example, work within the pharma industry, there will be certain things like, you know, Uberon and Mondo and other things like that, which are ontology oblique taxonomy constructs that are widely shared. And then what we'll do is deal with internal stuff.
I get it from an entity perspective, I think, within a company, but I just kind of wonder whether, you know, sort of taking that to, you know, as you suppose the word, and you brought up the organ kind of example in search, whether there's a.
Well, I mean, the alternative you see is that you've got numerous people, each with their own implementations of some sort of term clustering, and they're not shareable. You know, it's like, it's a social thing.
Yeah, no, I'm just wondering when the
technically it's not difficult.
Yeah, but that's just thinking in terms of natural language processing, the sort of solution that's happened is what is the large language model solution, which is to consider each word in its context, rather than thinking about.
So in the 1940s, didn't Indonesia have something like 700 languages, and then they decided it was impractical for the modern world, and we'll settle on one.
Yeah. So maybe back to GPT, the one solution.
Yeah. One here, what was that?
I think it was first, probably.
Yeah, just out of curiosity, just on what you said about unique identifiers, on it's like what it's completely out of curiosity. Does it involve if how you get to that term, the path you take is different in one ontology to the other? Because given the example of a cat, I mean, you can start with mammal, but I can start with
exactly
or animal leg.
And there is always see, I think the problem is that people started developing ontologies as greenfield sites, not real. Actually, one of the problems is that an awful lot of this started with people doing PhD stuff, and they created an ontology, and the next thing you know, this is up on some big public website and everybody's using it. Nobody's evaluated it really properly. And by that time it's grown legs and it's running around in the wild. And then you realize that somebody else is using a different one. And, you know, if you look at the bioportal, for example, you've got a ridiculous number of different ontological things, all started off as greenfield sites. And you still get it within enterprises, and you still even get it within W3C. It will start off like, for example, I'm in the dataset exchange working group and have some involvement with DCAT, okay? There are other ontologies, ODRL, DUV, Cube vocabulary, and all the rest of it. And apart from the RDF vocabulary, there's nothing that links the two, the three, the four of them together. And so nowadays, I mean, what ideally one would do is follow Fred Brooks' idea of building one to throw away and actually refashion a number of core things, all coming off a top-level core ontology. And in semantic arts, almost all our work is done off a single core ontology, which is GIST. And it means that what we can do in any enterprise is do one domain ontology and then another, and then another, and then another. And they'll all link together because they all descend from the core ontology. The way that we're having to do it at the moment is to sort of do lots of cross-mapping, and that's difficult because of two things. The first thing that we have is actually knowing sometimes ontologies don't have precise natural language definitions. And other times, what you're doing is having an ontological commitment with a big chunk of an ontology that you disagree with because it doesn't merge well with the rest of what you're doing. And so it's a problem. It's a problem for society. And we need, to be thinking as a society about how we deal with human communication that also involves machines when it comes to doing things that are important in our life, like looking after our health, like looking after our roads, like, all that sort of stuff.